So what is a bridge? Well, very simply, a bridge is a structure that covers a gap. Generally, bridges carry a road or a railway across a natural or an artificial obstacle like a river, a canal, another railway, or another road. The bridge is a structure corresponding to the heaviest responsibility in carrying a free flow of traffic and is generally the most significant component of a transportation system when traffic needs to be moved over spacings or gaps, such as bodies of water or valleys or gorges or other similar obstacles. A bridge is often the key element in a transportation system, as it controls the capacity of the system. If the width of a bridge is insufficient to carry the number of lanes required to handle the traffic volume, the bridge will become a constriction to the flow of traffic. If the strength of a bridge is deficient and unable to carry heavy truckloads, load limits will be posted and truck traffic will have to be rerouted. So the bridge controls both the volume and the weight of the traffic carried by the transportation system. Generally, it's the highest cost per mile of the transportation system. Bridges, very simply, are expensive. The typical cost per mile of a bridge is many times that of the approach roads to the bridge. And since a bridge is often the key element in a transportation system, balance has to be achieved between handling future traffic volume and loads and the cost of constructing a heavier or a wider bridge structure. If a bridge fails, the system fails. The importance of a bridge can be visualized by considering the comparison between two main components of a highway system, i.e. a road and the bridge itself. For example, suppose in a road there occurs deterioration, ultimately a crack in the road, thus making a sort of an inconvenience for travelers on that roadway. But it won't result in stopping the flow of traffic, as traffic can proceed or a bypass can be provided. Now, the traffic will no doubt continue to pass at a slower speed with some problems in the roadway, but in the case of a bridge failure, its flow is completely stopped. And that is the reason that it's often said that if a bridge fails, the system fails, as the function of the structure could no longer be served at all. Now, Federal Highway's definition of a bridge: a structure over water, roadway, railway, or other depression or obstruction with a track over it to move traffic. It's an opening measured along the center of the roadway of more than 20 feet between abutments. So, and there are a variety of different types of situations this might occur. 20 feet is not very long, so it doesn't take much of a stretch to qualify as a bridge. Type of bridge materials, just about anything you imagine: timber, reinforced and pressurized concrete, steel, masonry. Now, there are basically three major components of a bridge: the deck, the superstructure, and the substructure. The deck, of course, kind of distributes the loads to the substructure. It's the part that carries the roadway surface, obviously. The superstructure are all the parts of a bridge that are mounted on top of the supporting substructure system. And then we've got things like the pier caps, the piers themselves. It's kind of an example of the superstructure or a superstructure. And the substructure is what supports the superstructure and distributes loads to the ground. So your piers, abutments, spandrels, caps, bearings, and all the other components that hold the upper construction. All three components work together. Now, some of the common types of bridges, we have truss bridges, suspension bridges, arch bridges, slab bridges, or simple beam bridges, cable stay bridges, movable drawbridges, covered bridges, cantilever bridges. And with all bridges, there's two primary forces that are always applying pressure: tension and compression. And these and other factors are why we're going to be talking very soon about load ratings. And compression and tension are significant forces on any bridge. And if we have it calculated properly, the type of compression and tension that are involved, we could have serious ramifications down the road. Real life example, this was a permitted load, and somebody obviously did not do their math. Now, the significance of what we do when a bridge, when we as bridge inspectors, engineers, or superintendents don't get the math right or make an error in judgment, it could end up with more than just an embarrassing situation like that last example. Case in point, back in 2018, there was a bridge collapse in Florida. This particular bridge was on the campus of Florida International University down in Miami. Now, this particular situation has some personal significance to me, because in 2018, my daughter was in the process of trying to decide what college she was going to be going to. So we were traveling around the state and visiting various university campuses. The day before this bridge collapse happened, we were 50 miles to the north in Boca Raton and had visited Florida Atlantic University. And this day, in 2018, when the collapse happened, we were supposed to be on this campus taking a tour of Florida International University. But that morning, my daughter had said, "You know what, Dad? I don't think we need to go to FIU. I think Florida Atlantic is where I want to go." So we canceled our campus tour, a campus tour that may have taken us on this very pedestrian bridge across from the campus of FIU across 8th Street and into the town. I remember that morning driving out of Miami and hearing on the radio, right about the time we would have been on campus, possibly walking over this bridge, about the collapse. I'll tell you a little bit about what happened, how it happened, and what the results were. First off, you might find it interesting to note that there were some cracks that had developed in this bridge, and it was still in the process of being completed. It had just recently been moved into place. The construction took place in one area, and then we had mobile units that were kind of putting it in place, and they were doing some final touches. But here's a voicemail message that was left by an FDOT engineer who had done a inspection a couple days prior to this disaster happening. And here's the message the engineer left on a voicemail. "Well, we've taken a look at it, and obviously some repairs or whatever will have to be done. But from a safety perspective, we don't see that there's any issue there, so we're not concerned about it. From that perspective, although obviously the cracking is not good, and something's going to have to be, done to repair that." So that was the voicemail message that was left by the engineer who had just done an inspection on the bridge. It didn't seem to think that it was too big of a deal. Well, 2 days later, of course, it collapsed. Now, a little bit about this bridge. According to a fact sheet about the bridge on FIU's website, it cost $14.2 million to build. and was funded as part of a $19.4 million grant from the U.S. Department of Transportation. And it was designed to withstand the strength of a Category 5 hurricane. Of course, being in Florida, especially South Florida, that's a big deal. The fact sheet also said it was supposed to last for more than 100 years. Well, obviously that didn't happen. So here's a picture of the collapse. And what you don't see, unfortunately, in this picture, can't appreciate, is that 4 people died and many others were injured as the bridge collapsed and trapped numerous people that were in cars passing underneath it at the time. 4 people died, several other people were seriously injured. Bridge inspection and maintenance. The importance of the job that you and your crews do regarding proper and consistent bridge inspection and maintenance cannot be overemphasized. It could literally be a matter of life or death.